We're looking to make electric cars as light and as sustainable as possible to reduce their mass, reduce their materials, and maximize their efficiency. Imagine a motor so flat it looks like a metal pancake, yet powerful enough to shove a supercar forward in near silence. That sounds like hype, but it is real engineering. A British company called YASA took an old motor idea, changed the magnetic path inside it, and unlocked a new kind of performance. The company began as a spin-out from Oxford University, then became valuable enough that Mercedes-Benz bought it for future AMG electric models. Now the big question is simple. How can a thinner motor deliver more torque, run cooler, and even reshape car design right now too? The Oxford spin-out that turned heads. YASA was founded in the UK in 2009, built on the PhD work of engineer Tim Woolmer at Oxford University. From the start, the goal was not just higher power. It was better packaging. In an EV, every kilogram and every centimeter matters. A big motor steals space from the battery, the cabin, and the cooling system. So YASA chased a motor that could deliver huge torque without being a long, heavy cylinder. That decision pulled the company into the world of axial-flux machines, a layout that looks more like two discs than a barrel. As the prototypes improved, interest spread fast. Automakers and performance engineers care about two things: power density and repeatable production. If you can make the motor lighter, you also lighten the rest of the car because you can shrink the battery for the same real-world range. Cut enough weight and the whole vehicle becomes sharper. It accelerates harder, brakes easier, and uses less energy at cruise. That is why YASA's early tests were not just lab demos. They were aimed at real vehicles. From high-performance road cars to experimental platforms. By the time Mercedes-Benz acquired YASA in July 2021, the message was clear. This was not a science fair project. It was a powertrain advantage worth owning. Axial flux versus radial flux in plain words. To understand the difference, picture how magnetic flux travels inside a motor. In a typical EV motor called radial flux, the magnetic field moves outward from the center like spokes on a wheel. That geometry naturally creates a long cylinder. It is a proven design, and factories know how to build it at scale. But as you push for more torque, you often need more copper, more iron, and more length. You gain power, but you also gain mass and bulk. Axial flux flips the path. The magnetic field travels along the axis of rotation between disc-caped rotor faces and the stud in the middle. Because the motor is wide and thin, you can increase the effective radius without making it longer. And torque depends on force times radius. So a larger radius can deliver more torque with shorter end turns in the copper windings. Shorter windings can mean lower losses and less heat. YASA also emphasizes material efficiency. An axial flux motor can use less copper, less iron, and fewer permanent magnets than a conventional radial motor for a similar output. Less material can mean lower cost and a lighter, more compact package. Most importantly, the shape changes where the motor can live. Instead of a big central unit, designers can place drive units closer to the wheels or even consider one motor per wheel in certain concepts. Why this old idea was hard to mass produce? The funny part is that axial flux motors are not new. The roots of electric rotation go back to early experiments in the 1800s, including Michael Faraday's work. And engineers revisited axial flux layouts in the 1950s. So why did the industry stay loyal to radial motors for so long? The answer is manufacturing pain. Axial flux motors need a very tight, very stable air gap across a broad disc. If the rotor flexes, the gap changes. Efficiency drops, noise rises, and parts can even rub. Heat is another problem. High torque density means high current density, and snorts that creates hot spots. Many early designs struggled with cooling, especially deep inside the windings. Radial motors often use stacked laminations that are well understood and that helps control losses. Axial designs can be more complex to laminate in the same way, which can raise eddy current losses if the structure is not carefully built. Then there is the winding challenge. The copper in axial machines can be awkward to route, and if you can't automate winding, costs explode. Finally, tight tolerances at scale are brutal. Making one great prototype is hard. Making thousands of identical units is harder. For decades, that gap between the drawing board and the factory floor held axial flux back. Even though the performance potential was obvious to engineers, what YASA changed in the core design. YASA's progress came from solving those factory problems one by one. A major move was a segmented states approach. Instead of building one large stator ring as a single piece, YASA breaks it into smaller sections. That makes the parts easier to manufacture, easier to inspect, and easier to assemble with a consistent quality. Another key idea is the company's yokeless architecture, often described as a yokeless and segmented armature. In many motors, a heavy iron yoke sits behind the stud teeth. It helps guide magnetic flux, but it adds a lot of dead weight. In some designs, eliminating the seat yoke can cut stay iron mass by up to 80%. The reduced losses can also lift overall efficiency by around 5 to 10% depending on the duty cycle. By removing or minimizing that yoke, YASA can cut stay iron mass dramatically while still keeping the magnetic circuit effective through the careful geometry. The company also refined winding and assembly. Better winding processes reduce copper length and improve fill, which helps both efficiency and thermal behavior. On the material side, YASA has described using soft magnetic composite approaches in certain elements, where magnetic material can be formed and stacked in ways that suit the disc layout. Put together, these choices push power density up without making the motor fragile. In some vehicle designs, saving motor mass allows the battery pack to shrink, and the combined reduction can reach around 200 kilograms. That can extend the range and make the car feel lighter on its feet. Torque, cooling, and the numbers, people. Quote, YASA claims its axial-flux motors can deliver up to 4 times the torque of common radial-flux motors while being about 50% lighter and roughly 80% thinner. One widely cited example is a motor capable of around 480 horsepower and 800 Nm of torque in a package weighing about 24 kilograms. Those numbers matter because they change layout choices. A thin motor can take roughly half the volume of a similar output radial motor, which frees space for aerodynamics, crash structure, or extra battery. The torque story also connects to control. If you can package motors closer to the wheels, you can do torque vectoring more easily. That means controlling how much power each wheel gets moment by moment to improve traction and cornering. Electric motors also deliver near-instant torque because they do not need gear changes to reach peak twist at low speed. That gives EVs their punchy feel off the line. But none of this matters if the motor overheats. This is where YASA leans on direct oil cooling. Oil can pull heat out of windings and other hot regions with strong thermal contact that supports higher continuous power, not just short bursts. In many systems, a motor rated around 200 kilowatts may only sustain roughly half that output for long periods due to thermal limits. YASA argues its approach can hold much closer to peak levels, which is vital for performance driving, towing, and sustained high-speed running. Where it's used today and what comes next, axial flux is already in real vehicles. Ferrari's SF90 Stradale uses 3 electric motors with 2 independent motors on the front axle and a YASA axial flux motor at the rear positioned between the engine and the gearbox. That setup helps blend traction, response, and packaging in a tight space. Axial flux motors have also been linked with other exotic makers because they fit where a normal motor would force compromises. The technology also crosses into aviation, Rolls-Royce's spirit of innovation. Electric aircraft used YASA motors in its propulsion system, showing why power-to-weight matters even more in the air. On water, the same logic applies to high-performance electric boats and compact marine drives. YASA also argues that using less copper, iron, and permanent magnet material can lower both cost and environmental impact. After Mercedes-Benz acquired YASA, the plan was to scale production and feed the motors into future performance AV platforms. The most exciting part may be what the shape enables. A thinner motor can reduce drivetrain complexity. It can open space for better crash structures or more creative chassis layouts. And if one motor per wheel becomes practical for certain designs, then advanced torque vectoring becomes standard, not a luxury trick. In the next few years, the EV race will not be only about batteries. Motors, inverters, thermal systems, and software control will decide who feels fast, who feels efficient, and who feels truly new. So when someone says electric cars are all the same, remember this. Axial flux shows that geometry still matters. By sending magnetic flux along the axis, YASA made motors thinner, lighter, and easier to place where designers want them. The hard part was never the idea. The hard part was building it at scale with stable air gaps, smart materials, and cooling that can survive real load. Thank you so much for watching all the way to the end. If you enjoyed this deep dive, please smash that like button, share your thoughts in the comments below. And don't forget to subscribe and turn on notifications so you'll never miss a future update.